let's start with talking about some of the things that we had from last time. Right, so our first two lectures so far have been leading up to discussing what goes on in one-dimensional motion. And here is a very dense slide that has all of that information packed together at once. Right, there's a lot of things going on here, and let's kind of decrypt part of what we're seeing right here. We know that if you have any sort of object, particle, block, whatever you have, it might have a position and a velocity at some time. So position, x of I, velocity, v of I, time, t of I. Sometime later, at tf, we might have a different position and a different velocity. That's motion, right? And as long as we're confining this to one axis, those are all variables that we can use to talk about to describe how this motion is going to go. And of course, this seems obvious at first, but let's talk about some of the inner working pieces here. We see position, we recognize position, we see movement. That's a pretty easy thing to measure as well. The position can also be found by looking at how the velocity is affecting it, right? Or rather, the other way that we could do this is we could say, if I know how the position changes, surely I could calculate out what the velocity is doing at the same time. Now, looking at these two things, I could say, okay, well, that's one thing, but what about going another step? How do I know what the velocity is doing? If we know what the velocity is doing, we take another derivative down to find the acceleration. So each of these going to the right is a derivative, is the rate of change of the one it came from. Velocity being the rate of change of position. Acceleration being the rate of change of velocity. To go through those processes, we can do this one of two ways, but what we're trying to do is we are trying to take a derivative of our value. So if we take a derivative of our position, what we are doing is we are finding the slope on a graph, where analytically we are finding how the position changes, right? And last time we looked at how to do that both graphically and analytically. If we wanted to go the opposite direction though, if we already knew the velocity but we didn't know the position, then we could instead take an integral. And the integral is essentially doing just the exact opposite of what the derivative was doing. It's saying, okay, we'll take, you know how it's about to change, so surely you can calculate the total amount of change at the end of the day. Same thing you can do acceleration going to velocity. Both of these are an integral step up. And the two ways to do that are either you can plot out under the curve of what you're looking at. So if f of x was, for example, my velocity, and I knew that this is what my velocity was doing over some span of time, then the total area under that curve is my change of position. Similarly, if I wanted to do that acceleration to velocity, that works in the exact same way. If it's not such a kind blocky graph, then what I'm going to have to do is I'm going to have to analytically do it, and that's a little bit more complicated. So, let's do some review questions. Let's see how much you gathered from last time and how much that's sticking. Let's imagine here we have a cart and we see it is speeding up in the direction as indicated by that little green arrow. What do the velocity and the acceleration graphs of this cart look like? Which of these four options is going to match that? I think a lot of answers are sitting on C, what I've seen so far. But there is a little bit of variety in here. So let's talk about this. Let's go over this and let me explain my reasoning behind this entire thing. So part of what we need to do is we need to look very closely at what's going on in this picture. This right here is 0. This right here is not a value x, but it's like our axis, right? If we have a graph or anything else and you look at the two axes that are part of that graph, then I would have an x and a y. What is this saying? This is saying that x starts at 0 right here and trends to be positive in the direction that x is labeled. Y, similarly, is positive in the direction that it's labeled. So when we're looking at our picture here, that x is telling us this is the direction that we call positive. This way is a positive x. This way is a negative x. We are starting at a positive x value, we are moving towards 0, and I assume eventually negative x positions. So what that means is that if we are seeing that we're moving left, we are going in the negative x direction, I know right off the bat, my velocity is negative. Right? There's no way that it could possibly be positive. It has to be negative. So looking at answer A and answer B, not quite. Those are none of the things that we've got. So this one's out and this one's out. Now I'm going to be focused on C and D. Now I need to figure out what's going on here. So the velocity graph for each one is the same. That doesn't help me. I need to look at what's going on with the acceleration. Let's imagine here for a second. Let's take two different pictures. Let's imagine the cart in one instance has a little velocity like this and then has another velocity like this. So that's a V and that's a V. What direction must my acceleration be pointing? Left or right? What do we think? Left indeed. My acceleration is pointing the exact same direction as my velocity, and that's why my velocity is getting longer, right? It's becoming a larger quantity because the acceleration and the velocity are pointing in the same direction. We are speeding up. Speeding up does not necessarily say anything about the velocity on its own. It says that the quantity for the velocity is increasing, but it also says that whatever direction the velocity is going, the acceleration must be pointing the same direction. So in this case, since we know we have a negative velocity, we also know that our acceleration should be pointing left as well. Now, why it starts at 0 instead of being some value already set at a negative velocity, I don't think it's entirely clear or well written like that, but it doesn't necessarily say what the initial velocity was. To say that it's speeding up, you speed up from 0 to some velocity. So technically, the velocity graph here it doesn't contradict anything, but it just seems a little bit disingenuous to talk about a cart speeding up and then it starts at 0. But what can we do? How are we feeling? All right. Hopefully the descriptions and everything else have made this make a little bit more sense. Let's try something else. Let's imagine here, I've got a graph that looks like this. And there's a really key piece of information here that we start at a position x is equal to 0. If we start at x is equal to 0 at t is equal to 0 seconds, and we have a velocity graph that looks just like this, what is the position of the object at 4 seconds? Take 1 minute, think about it, see if you can come up with an answer here. All right, so I think I would agree that the answer here is C, but let me talk about how I got to that in the first place. So we are given velocity, but we are asked about position. So immediately, kind of off the bat, we got to be like, all right, so there's an integral involved somewhere, right? We need to go up the ladder. We need to go from the rate of change to the thing that actually changed. On its own, though, this graph does not give us enough information. Because what's actually inside of this, the area under the curve right here, is not x, it's the change of x. If we started at x is equal to 100 and then we had this velocity, we would move forward from 100. So starting at 0, we start at 0, we move forward by however much is contained inside of this curve right here. That's a very important distinction to be made. We don't know what the position is initially from this graph alone. We need more information. And if you're used to working with integrals, if you remember in the indefinite integrals, where you're asked to find, or whenever you finish the integral, you put plus c for some constant that might have been there, that's exactly what this is. That's exactly what this is. So, with all that stuff in mind, now what we can say is, okay, well, I know this is going to be the change of x, but I do also know what the initial x is. So as long as I can find the change, I'm golden. The way to do that, it's a blocky graph. So I'm going to cut this thing right down the middle. I'm going to say this rectangle over here is 8. This one right here is 4. right? For my top one, I've got 4 times 2. For my bottom one right here, I've got 4 times 2 times 1/2 because it's a triangle. For a total of 12 meters. That's our new position. The change of position will always be the area inside. The change of position. Here, since we started at x is equal to 0, those two quantities are equal. But if we had instead started at 4, then we would have been 4 plus delta x, 12. We would have landed at 16 instead. But here, since they tell us we're at 0, it's 0 plus 12 is where our position is now. So I have a question for everybody. What if they asked us instead, what is the position at t is equal to 2 seconds? What would our answer be then? Eight indeed. Just because you have the full velocity graph does not always mean you are going to use it. If they asked for the position at 2 seconds, what you would say is, cool, I know that we are going to keep traveling forward as time goes on, but I'm not there yet. So far, we have only moved through this area. That's the only part that would count. We would have been at 8 meters per second 2 seconds in, 8 meters 2 seconds in. If we waited the full 4, that's when we land at 12 meters. So keep that in mind. You might have a variety of problems here that ask you for different things. Sometimes they might tell you what the position is at 4 seconds. You might not know where you start, but you know where you end. Sometimes they might tell you your position somewhere right in the middle, like at 2 seconds, and then you've got to figure out where you started and where you ended. A lot of those details might be missing in some of these things, so keep that in mind. Using pictures, drawing on these things is a very, very, very helpful thing. There's a reason that we draw so many pictures. It's useful. So, I've got one last one for us here. Let's imagine we have this position versus time graph. Which of these velocity graphs do you think matches that picture the best? Take a few seconds, think about it, maybe draw on it if you would like to. Answers. And it's not always that my multiple choice questions are always going to be answer C, but that's just how it kind of landed today. So let's prove it though. Let's go through all the steps here. So I'm going to try and break this into kind of 3 segments. If I take this thing, I can say, hey, towards the end here, that's kind of flat, right? That's almost flat. Being almost flat, staying in the same place, I don't have a velocity, right? Or at the very least, I'm tending towards 0. I'm about to hit 0 in my velocity. So I look at that and I say, okay, that's not 0. That's not 0. Neither of these are giving me what I'm looking for. Velocity is not equal to 0. Let me look at the other segments. Let me split it right around here or so. While I'm in this section, that looks pretty linear to me, right? I don't see any real curve to that portion of the graph. And if I'm seeing a linear function, a constant slope, if velocity is the slope of position, then I'm assuming that v is some constant through that span. What direction is that constant going? Positive or negative? How is our position changing? Any guesses here? I mean, I'm assuming that everyone who has answered C probably knows this already, but I like to see that little bit of extra reasoning just in case. It is a positive slope, right? Just because the position is negative doesn't mean that we don't have a positive slope. Remember, those values can be independent, right? They influence each other, but what they are at any given moment does not mean anything about the others. Here, position is negative, velocity positive. We're trending towards positive numbers. So when I'm looking at D right here, this says we're going down. Our slope is down. That's not it. C is the answer that makes the most sense. Also, a fun trend that helps some of these things, if you have a long question or anything else, if you are not a particularly fast typer, one of the things that you might be able to do to help with this is if you have a question that you're about to ask, save myself a little bit of time here. Write out question real quick and submit that. And if I see question pop up, then I know something's coming and I can give it a minute, let you type out that question before trying to rush through this thing and try and get something out there before I start to move on. So it just makes the whole thing a little bit easier. If you type that first, send it, then I know to wait. Otherwise, we can move on a little bit faster if there's nothing else that we need to talk about. So, and I forgot to erase some things. The little bits right there. So most of the time, as we are talking about these things, we are going to be looking at a lot of different scenarios where we have a constant acceleration, which if you have taken any sort of physics course before, looked at any sort of physics material, you'll probably have seen this last time too, right? Acceleration being a constant value is one of our most common things, and there's really a couple different reasons. One of them being it's so much simpler. Like, let's be real. This equation that we've got right here, this is already 3 terms. That's a little bit involved, I think. If we wanted to add the next derivative down, if we wanted to, or if we knew what the jerk of a scenario was, right? If an object was experiencing some jerk, the third derivative down, then we would get an additional term that looked like this. Does anybody see that pattern? Does anybody know what would the next one look like? I can go with that as well, and I'm trying to remember what it was. It's jerk, then snap. So let's call snap, I'll call it N, for example, because we've already used S somewhere. They're integrals each time. Right? That's the process that this goes through each time. And by the time you have seen acceleration, I think that's a little bit more obvious. Right? I remember when I first when I first started looking at physics material in general, when I saw this equation, I had taken calculus already. So I looked at this and I said, hey, wouldn't you know it, that's like an integral pattern almost, right? That's the pattern if I wanted to do integrals or derivatives down or something like that, I would get the next thing in the sequence. So why I'm saying this is because if you're worried about this, if you are going to be in a scenario where you need to worry about these further down derivatives of motion, you'll know what to do. You'll have dealt with acceleration and you say, well, I know it's just a bunch of integrals and derivatives, and I have already mastered the first 2 of those. What's adding on one more, right? What's a derivative between friends? Getting to that point will be much easier. Part of the reason as well is because, it's kind of unnecessary, but also this is now 1, 2, 3, 4, 5 terms. Do you want to deal with 5 terms and probably 6 kinematic equations? Is anybody going to volunteer for that one? I don't think so. It is much easier to look at the simpler scenarios for now, to master the easier cases, and then when you need to move on to the more complicated pictures, you will have already practiced everything you need to do that. You'll be all set by then. But for now, we're going to stick with the easier things. So in looking at these equations that we have right here, you might notice that 2 of them look kind of similar. One of them looks a little bit different. The top one, we see a pattern of derivatives and integrals. The second one, we also see that pattern, even though it's not complete yet. Right? Now we have essentially, here is how much has my velocity changed by taking the rate of change of the velocity and multiplying it by how long it's been changing. So again, we could add more derivatives onto that if we really needed to. The last one here does not follow that convention, and it will not. Knowing how these things work together, how integrals and derivatives relate to each other, does not help you derive this equation. And in fact, we're not going to derive this equation for another few chapters yet. But we will soon enough. For right now, what I want you to do is just take me at face value for these things. Assume these equations work, or at least you can prove the first 2 do. Assume that the third equation works just as well as the others. And one day, I will prove that to you or give you the tools to prove it to yourself that this equation works. Fantastic question that I haven't addressed. What is S? S is a stand-in variable. If you remember when I was talking about position, we said that velocity is usually v. acceleration, v is equal to velocity, a is equal to acceleration, and that's a pretty consistent thing, right? But what about position? Position could be r, it could be s, it could be x, it could be y, it could be z. Why do we do this? I don't know, because we're monsters, I guess. There's a lot of different things that might represent position, and what it's really going to come down to is this is a placeholder variable for now. Today, when we solve these problems, I will not be using s, I will be using x or y. And it really just depends on the axis. Because realistically, that equation right there, it works in the x direction, it works in the y direction, it works in the z direction. If you want to take some weird oblique angle, I would call that the r direction. It would work in the r direction too. This equation works everywhere. So rather than having a new equation that looks identical for every single axis, we just say, hey, this is the equation that you use for motion. And then whatever direction you're going, you've got it. Save some paper space. So I want you to try and use this one. Let's say a speed skater is moving along on nearly frictionless ice, traveling at a speed of 8 meters per second, but then hits a 5-meter long patch of rough ice. Ice that is not so smooth, ice that slows her down at a constant rate. By the time she gets through the rest of that rough patch, she is now moving at 6 meters per second. What was her acceleration while on the ice? Now, I have some problem-solving advice. I know a lot of people are not going to listen to me this time, and that is okay. I know a lot of you are already putting in numbers into those equations that I have just shown you, and then you're going to try and calculate these things out with calculator in hand, writing down the new numbers at every single step. I'm going to recommend against doing that. And I'm going to tell you that that is what I did when I came in. I used numbers for everything. And 8 years of experience later, I do not use numbers. There's a reason for that, right? It's not just because I like writing letters more than I like writing numbers. I like writing letters and variables because it's easier to solve with. It stops you from making a lot of mistakes, it saves you from a lot of different grief, and it makes your solutions more general and easy to read. So what I'm going to suggest that you try doing here is solving this with variables, and at the very end of the problem, plugging in those numbers. And I'm going to go so far as to help you with that process right now. This 8 meters per second, call that our initial velocity. 5-meter long patch, call that delta x. 6 meters per second, call that our final velocity. And if you weren't sure how to start this problem, go back and look at the last 3 equations that you've just been shown, and I think you might see how to get through this now. Makes this whole thing just a little bit easier to read. So, take the next 2 or so minutes, come up with an answer here. Okay. Let's start to take a look at this, and let me talk to you about my process for going through a lot of these. So right now, if you have looked at the equation sheet, you will see that there are maybe over 100 or so different equations to use. One day, you cannot just write out all the equations that you know and look for the one that works. But right now, we've only got 3 to worry about, and so this method, this strategy will get you through at least the beginning bits. Here's what I'm going to do. I'm going to take this idea, and what I know so far, I have been given a few different things. I have been given an initial velocity, a final velocity, and a distance that some sort of deceleration happened over. I'm asked to find what is that acceleration. The first thing that I'm going to do is I want to try and draw some sort of picture out here to help me, because this has given me nothing, right? I don't have anything to look at to really try and organize my thoughts over. So instead, what I'm going to do is I'm going to think about this to say, okay, well, if we have some sort of graph, and we know about the velocity, so let me draw a velocity graph. Velocity, versus time. I know she was moving at a constant velocity over frictionless ice, constant speed. Then, at the very end of this, she was again moving at a constant speed, right? But in between, there was this rough patch that slowed her down. This is not drawn to scale. You don't need to draw these to scale. I'm not putting numbers on any of these things. This is here to help organize my thoughts. This slope right here is my acceleration. So right off the bat, what do I know for my slope? Is it positive or negative? Negative. Yeah, I see a negative slope here. I expect to see a negative acceleration. Now, I'm going to think about what are my kinematic equations that I have. Here is one such equation. And I'm just writing t instead of delta t, but they mean the same thing here. So I've got that. I also have this. And finally, I have this. So what I'm going to do is I'm going to go with this thing piece by piece. And I'm going to say, okay, let me highlight what I know, what I don't know. Delta x. Delta x we know is final minus initial, right? That's what a delta means. X final minus x initial. So if I subtracted x initial over to the other side, that's delta x, right? So I'm not going to consider those to be unknowns. I think I have that. But I don't know how long we were over that patch of ice, and also specifically we are looking only at this part. You know, constant velocity before that, we don't care about. We only care about what's going on in the middle here. I don't know time, I don't know acceleration. That is two unknowns in one single equation. Is that solvable? Yes or no? No, it is not. And this is a theme. Right now, we're typically not going to deal with a whole bunch of different systems of equations, but you always need to have as many equations as you have unknowns. Otherwise, you're not done yet. You can't solve anything. So I'm going to say, okay, not very helpful for me right now. Okay, well now I look at the case where I have the final velocity, I have the initial velocity, I'm looking for the acceleration, but again, I don't know time. It doesn't help me. It's kind of closer, I guess, but it doesn't have enough information. I look at my last one. I have final velocity. I have initial velocity. I have delta x. A is the only thing that I don't know. This is our golden ticket. This is the one that we're going to use to solve this. So what we can do then is I'm solving out for A, and I'm going to keep this stuff in variables for now. First things first, I'm going to move over that velocity term. We're just in algebra now. The physics is done. Now, I'm going to divide by the pieces that I already know. My acceleration. Now I plug in my numbers. Now that I've got everything else in here. Let's do this in like a dark red. So our final velocity, 6 meters per second squared, is going to be 36 minus 64 divided by 2 times 5. At the very end of the day, we end up with a negative 2.8 meters per second squared as our acceleration, which is indeed the negative number that we are expecting to see. To the question, so S is X now. Yes, S, remember, is a stand-in for any variable that we need it to be. It is position. So in this case, we're talking about moving in the X direction. So I'll say my position is all X. If we were instead moving in the Y direction, then it would be Y. We only have 3 equations right now. So if we're trying to figure out what equation we're going to use, we essentially just look through the 3 of these currently and we say, hey, which of these is solvable? In this case, the first 2 equations didn't work because in either of those, I had 2 unknowns, and that's not a solvable equation. Our last one, we only had the 1 unknown. So that implied to me that, hey, I could solve out for this variable right here and right now. I don't need anything else. This equation gets me there. S can be X, Y, Z, or anything. It's just whatever direction we're moving. S implies position. I didn't write V of 0 anywhere, right? Okay. I did. Shoot. V0 does imply initial. Yes, I like to write, that's actually called V0 is the actual name for it. Here's a little bit of an extra thing. So this is, I would call this V, and it's pronounced not, spelled like this. It means initial. It's another way to write initial. It's what I typically use. I don't like to write more I's in places because I have dealt with things. If you deal with quantum stuff, you have a lot of imaginary numbers floating around. So I don't like to put more I's than I need to. V0 is something that's a little bit more consistent for me. But yes, they mean the exact same thing. So I really, really, really can't recommend solving with variables enough. It is a very wonderful thing to have, and I know a lot of people are going to stick with numbers anyways because numbers are probably what you've been doing this entire time, and you're used to working with numbers, and what's wrong with numbers? But it just, from experience, I will plead with you. Doing this is easier, it's faster, it's less writing, it's less prone to mistakes. It's for your own benefit, I promise. And I will continue trying to convince you. If you are not yet already convinced, I will continue trying to convince you, and I imagine that most of you will be convinced by next semester at least, but it might take a little bit of time. I realize that. So apologies if you are already converted and you think it's ridiculous that I keep bringing it up. So I want to look at another one here, and this time around, it's a very similar looking problem, but I am not going to scribble out these variables for you. We have a jet plane that starts at 300 meters per second. They turn on the afterburners or something, they go full throttle, traveling 4 kilometers, and at the end of this 4 kilometers, they are now at a speed of 400 meters per second. What is the acceleration of this jet? So if you're following my advice, what I'm recommending here is that you figure out each of these numbers is a variable. Which variable is it? Organize it effectively, and then look and see which of the 3 equations that we have would really help us solve this problem. And just in case you're looking for those, I can put those here again. Stop giving me design ideas. I know how to make my slides. There we are. So I'm going to say take the next, again, 3 or so minutes, then we'll take a look together. Maybe even just 2. All right, I'm starting to see some of these answers flood in, so let's take a look together. And remember, a lot of the point of these things, if you find yourself struggling to get through in like a timely manner, and I'm saying a timely manner here, right? Working at your own pace and everything else. I don't want to try and rush you along or anything else. The reality is that we have a certain amount of time, and as much as I would love to have one lecture that lasted 4 hours, I would not love that, by the way, but let's pretend that I would. I can't imagine that you guys can sit through that comfortably and keep working at that same productivity the entire time. You know, we need to shake things up. We've only got a limited amount of time, and I really don't want to push that too much more. So my point here is that if you are getting started with the problems and you're making some good progress and you see where the problem's going to go, you are still in a golden position. I'm not worried about that at all. You know, this way we don't have anyone just kind of fumbling for a long period of time. If you're really not sure where to start, as long as you're making progress and you know where the problem is going, that is exactly the scenario that I'm looking for here. When you get to the homework, you've got as much time as you need on those things. So, what we have here, describing what's going on with this thing. We say we start, and actually let me go back to the slide here to talk about these things. Part of the task here was figuring out which variables are what. We're cruising at 300 meters per second. We have a velocity. What velocity is that? I'm not sure yet. When suddenly the pilot turns the engine up to full throttle. So we were going at 300 meters per second, then something else happened. This right here is my initial velocity. Traveling 4 kilometers, the jet is moving with a speed of 400 meters per second, and that's the end of the problem. So this right here is my final velocity. The 4 kilometers was what happened in between. That is a delta x. So we think about this thing, we say, hey, wait a minute. I just saw this. You're not pulling a fast one on me. I see the exact same given variables as last time with the exact same prompt to find the acceleration. Here, though, we see an increasing velocity, so we expect to see a positive acceleration. But one last thing that I've got here. What is my change of distance? What did I just say? What should we actually write down? What do we think? 4,000 meters is exactly the correct thing. 4,000 is our standard, or meters, I should say. Meters is our standard unit. Kilometers is not our standard unit. So the first thing that I need to do is I have to make sure that all of my units in the equation agree. That was not a problem that we faced in the last problem, right? If we go up to this thing, we see, hey, meters per second, meters per second, meters. One of the things that we can do to make sure that we solved everything out, correctly at least, is we can check what units we have in each of these places, and if the units make sense, if all of the units agree on the left side and the right side of the equation, we're golden. We probably did it right. If the units don't agree, then we need to take a closer look at what's going on. So we're given these things. We're tasked with finding the acceleration. We already know what equation to use. We just saw it last time. It's the exact same equation for the exact same reasons. We don't know what time is. Without having time, those other two equations aren't so useful. But having a distance means the last one is. Vf squared is equal to Vi squared plus 2a delta x. I'm going to rearrange. I am interested in finding this a right here, so I'm going to solve out for it. Do a little bit of algebra. My physics is done. Vf squared minus Vi squared divided by 2 delta x puts me equal to A. We plug in all of our numbers, and what we should find at the end of the day was, I think I knew what this was, but I want to make sure that I don't write down the wrong number, 8.75 meters per second squared. And that's what we've got. How are we feeling? What questions do we have? Or do we have any? Are we feeling all right? Okay. So, as we're looking at this thing, let's go ahead and take a look at our next topic for the day. The entire point of this thing, free fall. Falling, right? So, you probably know this. Hopefully this is your last lecture of the day after a long first week of the semester, because I know for whatever reason, spring semester, that first week hits a little bit harder than it does in the fall. Hopefully you're getting some well-earned relaxation later on, and I imagine you're probably going to experience a little bit of free fall as you flop down onto a bed after this. Right? What is actually doing that pulling? Well, you have probably heard for a very long time that it's coming from Earth. There's a gravitational pull from Earth, and that is one of the 4 fundamental forces pulling on you if you really want to go that far. We're not talking about forces yet. Not yet. We will very soon here. But in the meantime, what I'm going to try and do is convince you that there is an acceleration because of gravity. Let me turn this whole thing real fast, and this messes up my screens every single time, but for the sake of the demonstration, we need to have it. I have in my hand a very old USB charger. Not a feather, not anything crazy like that. That's going to be very light and not react or anything else. If I hold this in place, what is the velocity of this thing right now? 0. I would agree with that. So can we all agree then that when I do this, When I release it, nothing actually changes. I'm not throwing it down into the ground. I'm not doing anything to the velocity. I am letting it do whatever it wants to. If it floated right there, I didn't cause anything to happen to it, right? My interaction, as soon as I release, my interaction with it is done. So let's test it, and I'm going to try and mute myself here at the instant that I do this to not cause any sort of headphone problems or anything else. What a surprise! It fell down, right? That's not anything crazy. The acceleration from that caused it to gain velocity, and it continued speeding up as it fell down to the ground. I am sure you guys have all heard of things like the penny off of the Empire State Building can kill somebody. And I think they disproved that one because the air resistance or something, but things like that, right? Things speed up as they fall down. That implies to me that Earth is not causing a velocity, it's causing an acceleration. And the acceleration is causing that velocity, but it's not a constant velocity, it's a constant acceleration. Another big reason that we deal with constant acceleration and not with jerk and everything else. Because one of our very common problems, throwing things or dropping things, has a constant acceleration associated with it. So for us right now, we are not going to be worried about the gravitational force. We are going to be worried about the acceleration because of that force. Where we are at in Ohio, and I imply we in Ohio because remember, it's all Ohio, always has been. The acceleration because of gravity is about 9.8 meters per second pulling down. So we have a variable here, g is equal to 9.8 meters per second squared. (9.8 meters per second squared, not negative 9.8 meters per second squared. Here, the acceleration is equal to negative g, negative 9.8 meters per second squared. But I'm specifying this. This is the convention that we are going to use for this. G is always a positive 9.8 meters per second squared. Whether or not that is negative depends on what we are calling up. I would make jokes about Australia, but I'm worried that that joke wouldn't land with everybody. So for now, what I'm just going to try and tell you here is that our acceleration when we're dropping things is a negative 9.8 meters per second. That is negative g, specifying that y is pointing up. So this might imply we're using some new equations. And I want you to try using some of those new equations because we have a rather ridiculous scenario. Before, the manufacturing process for steel ball bearings does not work like this. But it technically could have at some point in time. Let's say you are trying to recreate an ancient method of creating relatively equal-sized ball bearings. The way to do this is you take molten drops of metal and you drop them, and as they fall on everything else, they form spheres, and they solidify before smacking into the floor where somebody sweeps them up. To do this, you're going to create a very tall tower. Each of these molten balls of steel is going to need to fall for 4 seconds to solidify, or else if it's still molten, then it's going to explode and probably cause burns and you'll get sued or something else like that, right? So you're the engineer trying to design this thing. Naturally, there is construction costs associated with building this tower. So your employer has asked you to build this tower at the minimum height needed to achieve this. So you can't just build a tower that's 100 million meters tall. That doesn't work. What you're going to need to do here is to find the exact height that the tower needs to be so that you can drop the steel ball, it's going to fall, and it's going to hit the ground at exactly 4 seconds. Once you have that height, then I want you to look and see if you can find out how fast is the ball going to be falling right before it hits the ground. So I'm going to say it's probably a good time to start taking a look at this thing, and I'm seeing an interesting split. There are 2 answers I see for part A, 2 answers I see for part B. So let's get to the bottom of it and see which one it is here. So first thing we need to do is we need our tower, right? I'm going to draw a picture for this thing because this is probably going to help me visually represent what's going on here. So let's imagine we've got a tower that looks kind of like this, right? Classic, well-built, good construction. We start with a molten ball of steel at the very top. At the very beginning here, does it have any velocity? What do we think? Probably no velocity, right? And we'll deal with the roof later. We need to build this thing first, and we need to build the body. This is where it's going to be dropped from the first place. But we're kind of doing a similar thing, right? I'm just like holding it out, and let me get it a little bit closer. I'm releasing, right? I'm not throwing it down. That doesn't work. That doesn't help anything. I'm not tossing it up or anything else like that. I'm just releasing it from rest, allowing it to fall down. So we can imagine that as time goes on, this thing is probably going to fall something like this, until at the very end here, the instant right before it lands. And I'm talking about the instant right before it lands, not necessarily as it lands or anything else. There's a little bit of nuance here. Let me finish this thought. But right before it lands, it has a velocity pointing down like this, right? It's just been falling for a while. It should have a velocity associated with it. It also has a final position. Now, the nuance of looking at it right before it hits the ground is very important, because imagine what happens once it does hit the ground. Dropping something is pretty simple and uneventful, if I'm being completely honest. As long as we're neglecting air resistance, and air resistance for the most part is not a big deal. It does not come into play in anything that we're doing here. But once it hits the ground, it is going to have reverberations going through it. It's going to suddenly change direction. If there was a speckle of dust, maybe it bounces off at some oblique angle. There's sound, there's energy, there's vibration. And talking about all of those things, you might be able to kind of gather that's a complicated part. That's a really complicated part. Such a complicated part that we are not going to talk about anything like that for some time. We are not going to look at the instance where it is in the middle of colliding. We are going to look at the instance where it is a nanometer above the floor, right before it collides, because everything after that is a little bit different, a little bit more difficult, and we need some more tools before we can talk about that. For now, we're going to focus on while it is in motion before those collisions happen. So my last thing that I'm also going to do is I do need to label my picture, because what is actually up? Again, is this built in America or is this built in Australia? Is it pointing up or is it pointing down? For the canvas question, I have said that Y is pointing up. So what that means is that when we're thinking about all these different things that we have, we know at the very beginning that my initial velocity is 0. It's being released from rest. We also know that I'm assuming here. Let me say that. Let me say that I'm building this tower on the ground. I'm not building this up in the sky. I'm not building like an underground bunker so I can make ball bearings in a method that's been outdated for decades. Instead, I'm just going to build this somewhere out in a field. And that means that this value right here, YF, is equal to 0. This is going to make this whole thing a little bit easier. And I'm going to talk about the decision in a little bit. What else do I know? I know that it has to have been falling for 4 seconds. And is there anything else that I've got? V initial, Y final, T. I know one more thing, and what is that one thing? I'm looking here for it. What other information do we have? Oh, the last bit, the most important one. What makes it fall in the first place? The acceleration. We know that it's accelerating because of gravity, and it's doing so at a rate -g. So now that we're here, let's think about the things that we need to find. We need to find how tall is the tower? At what height was it dropped from in the first place? Then part B is asking us to find how fast is it going right before it hits the floor. So what I'm going to do, I'm going to take the same strategy. I have all of these different equations, but there are only 3 that we're actually working with at this moment in time. So let me start with this one. Not Y initial. Y is our position in the Y direction. Kind of like how most of our graphs are X and Y. It's kind of a standard to call the vertical axis Y, the horizontal axis X. Here is one such equation. And keep in mind, I know my acceleration is negative, but the equation is plus A. Right? So that negative sign will come in place when I plug in for that value. I also have an equation that looks like this. And finally, my last equation. So I'm going to take the same process right now, and I'm going to look at these equations, and I'm going to ask myself, what do I know? What don't I know? Are any of these equations actually useful for what I'm trying to do? So I know y final. I know it's 0. I don't know y initial, but I am searching for it. I do know the initial velocity, and I do know the acceleration, and I know the time. This equation right here only has one unknown. That's supposed to be a check mark. It only has one unknown. That's solvable. But let's look somewhere else first. Let's see if there's anything else that might help us as well. I look at my second equation down and I'll say, okay, well, v of f, I'm looking for that eventually. I have the initial velocity, I have acceleration, I have time. That's the only thing I don't know in that equation. That's a solvable equation. That's ready. What about my last one? I don't know v of f, I don't know delta y. I'm not going to use this one. It seems silly to use it when I have two ready-made equations already here on the side. What would make, so g, remember, is positive. The acceleration being positive is a choice that I could make, but let me get to that in a second. Let me finish that. Let's finish the problem, and then we'll talk about some of the nuances here that we could have picked. So I'm going to start with finding y of I, the initial height, because that's part A of the problem here. So what I'm going to do is I'm going to write y of f 0 is equal to y initial plus v initial times t 0. No problems there, and I'm just going to plug in g while we're here. Now, this is really easy. We've eliminated 2 of our 4 terms. We've only got 2 left. Y initial is equal to 1/2 gt squared. So I imagine there might have been a little bit of discrepancy. A lot of people looking around and plugging in those values. If you found 156.8, did you remember this 1/2 at the beginning? Because that's a pretty important bit. But when we plug it into the very end of the day, what we should find is a 78.4 meters tall. So, for part B, similar things apply, right? And this one's even easier because in this case, it's already solved out for us. There's no rearranging that we actually need to do. We're looking for VF, and it's right there on one side of the equation already. Our V initial is still 0 minus GT, which is an important point. Our velocity is negative 39.2 meters per second. And why is it negative 39.2 meters per second? Because it's going down. We said y goes up. The velocity is going against y. The velocity must be negative. The acceleration is also negative. This is where some of the nuance comes into play, though. Because I didn't have to decide that y goes up. This is convention. It's typical. But I could have made some other decision. I could have instead said, I don't like that. I'm going to say y goes this way. And some of my values would change. We could have been in Australia where everything is upside down, right? Some of my values would have changed because of this. Now, y initial would have been a negative value. My velocity and my acceleration would have been positive values. Everything gets flipped around. But ultimately, at the end of the day, we come out with the same answer. We would have found a positive 39.2 meters per second as our velocity, but we would have looked at our picture and said, hey, isn't that saying the same thing? Right? Isn't the velocity still pointing down? Isn't it going into the ground like we expected it to? Yes. So even if we're off by a positive or negative, a lot of the time that's not a really big issue because we just have to go back to our picture. And this is what makes a picture invaluable. Because if you make these decisions, if you decide one direction is positive, one direction is negative, you have to stick to that decision. If you back out halfway into the problem, having already made that decision, and you switch it to something else, it doesn't work anymore. You're going to get the wrong answer. Maybe you can finish doing the math, but it's not going to be right. So this is part of why I like to draw pictures as well, because this forces me to pick something and stick with it, right? If you're not entirely sure what direction to go with, it doesn't matter. Pick one, carry it to the very end. If at the very end you said, hey, that was stupid, that's got a lot of negatives, then, I don't know, you can flip it around at the very end after you've solved it. But when you are solving a problem, follow your picture. Stick with it. So, one of the last things that we've got here, right, the last new topic for the day at least, is let's imagine here you've been working on these things and hopefully you have not been getting too tilted so far with dealing with a lot of these problems. But we can imagine here, we saw me drop this thing earlier, right? And let me demonstrate this thing again. If I demonstrate this thing so far, and let's get like a very, very, very rough timing to this thing. It's standing just a little bit above, and I drop it. That's not a very high thing, right? What if instead I'm on a slope? And let's assume that there's not like a ton of motion or anything else like this. But if I'm on a slope, did that fall as fast? No. Generally speaking, I don't think so at least. And I think if we had a longer slope to actually demonstrate this, this would be a little bit easier to do. But the same height might have been fallen, but because we're on a slope, the slope is kind of stopping you from falling down, right? It's slowing the whole thing down the entire time. So our acceleration no longer goes as 9.8 meters per second squared towards the ground. Instead, it scales with the angle of the slope. That angle right there, theta. What we're going to have in this one is that our acceleration in the x direction as we have this thing labeled. So if x is going down the slope, right, everything's tilted a little bit more like this now, right? Now we're not just looking at horizontal and vertical, we're tilting our axes a little bit. So x goes like this, down the slope. Then our acceleration down the slope goes as g sine of theta, depending on the angle of that slope. For now, don't worry about friction. But this is our classic block and slope problem, which there it is when the show names itself. So this is what we've got. All of our equations that we have just been dealing with are the same, right? There's no real difference between any of these pieces or anything else. Our acceleration term just looks a little bit different, but you'll notice it's still a constant, right? We are not constantly changing the slope. The slope is set. We drop the thing down it. So let's try this out. Let's imagine a skier starts and they're going level, 3 meters per second, then hits a slope, starts going down. Naturally, they speed up as they go down the slope. The slope has a 10-degree incline. So that theta is 10 degrees this time. His speed at the bottom of the hill is 15 meters per second. Got two things. First, what is the length of the hill? Like, how far has he traveled? What is that stretched length down the side? Not the height or that kind of deal, but like how far did the skier travel? Second, how long did it take to get from the top to the bottom of the slope? So I'm going to give you guys about 5 minutes or so, and then we're going to take a look at this one together. Are people not just remembering every single integer degree value and what sign would be of that integer? We can all assume that I'm joking with that one. But while I'm talking about all this stuff, I'm going to say it's probably a good time to start taking a look. So I do want to draw a nice little picture for this thing. Let me find myself a little bit of space here. What about right over here? And I'm going to draw just a little bit of before and after with what I'm seeing going on in a picture like this. So we've got something like this. We had our flat slope, our slope, back to flat. And I'm zoomed in a little bit more than I intended, but that works, right? And then we have like the flat angle right here relative to the ground. This is our 10 degrees. So what we've got, some of the extra pieces here, is this length right here is my delta x. Right? That's one of the pieces that I'm actually looking for here. I'm going to need that one. And then here is my skier. Bundled up, I assume. Moving at a velocity initially, v0. And I know that I'm drawing them like still on the horizontal part, but let's assume that it's about to go down. Something like that. Here they are at the bottom, their velocity having again gone along this direction. Let me draw this a little bit longer. I need to rotate or else I can't draw this properly because I can't draw properly at all in the first place. So I'm trying to draw this thing just a little bit longer than our initial velocity, just so we can have a relatively set value here. And the last thing I should have done here before I actually tilted that back is while I'm at it, while we want to do all this stuff, we do want to get into this really good habit here of labeling our axes, thinking about what direction all of this stuff is supposed to be going. So I'm looking at a velocity, two velocities, position change, all of them pointing along this axis right here. It's an important bit, right? So what I'm going to do is I'm going to draw that arrow and I'm going to say this is x, and that tells me what my positive direction is supposed to be. So between all of those things, now we've got a good picture. We've got a good sense of what's going on with these things. Let's talk about what variables we have, what variables we don't have. Given our initial velocity was, 3 meters per second. Our final velocity, 15 meters per second. What else do we have? We know that the angle, the angle is 10 degrees, and that's all that we have right now. And that should be enough. I mean, also, given that we have the angle, 10 degrees, acceleration, g sine of theta. And so this is one of the big reasons that we don't just say g is negative 9.8, because here, our x direction going down the slope, the acceleration is positive. It's going in the direction that we have called positive x. So that's why we like to write g as positive 9.8, because then it's a little bit more versatile. So, finding two things. First, delta x. Second, time. How long did it take to actually get down there? So, let me look at my equations one more time, and let me say, okay, with these three variables, I'm not going to count theta in here. I'm going to say v0, the initial. I keep trying to, sorry, my habits are hard to break in this one. I'm going to try to do v initial whenever I remember it, but I'll probably forget sometime. So seeing v0, it means exactly the same thing, the velocity that we started with. So as we go into this thing, I look at these equations and I say, okay, I need time eventually, but I don't have it now. And then one of these things minus the other, that's like a delta s. I could potentially work with, there's two unknowns in that. I can't do that. The second one down. Well, that might actually be something worthwhile. Let me write that out real fast. Let me see what I've got in that. Had we written VF is equal to V initial plus A times T, and I highlight what things I don't know, T is the only one. That's solvable. However, that's part B. And I'm going to get to that in a second here. I want to focus on part A, and part A is going to suggest instead that I use my last of the three equations. VF squared is equal to VI squared plus 2A delta x. I look at this and I say, I know what the acceleration is supposed to be. I know what V final and V initial are. The only thing that I don't have, and exactly the thing that I'm looking for, is delta x. We're ready to solve this thing out. Let's rearrange some variables here. So let's say VF squared minus VI squared, right? And that would put that on, let's just go through these steps just in case. 2A delta x. While I'm here, let me plug in my A. 2g sine of theta delta x. Delta x is exactly what I'm looking for here, so let's solve out for it. G sine of theta. Plug in all of those fancy numbers that we have just pulled from the last thing. And what we should find at the end of the day here, and let me check my numbers to make sure that I'm not just writing down hot nonsense, 63.45 meters, as I have it. 63.45 meters as our distance down the slope. So and from the very beginning here, we kind of said, hey, we found time first. Delta x generally going to resemble distance traveled. It's a change of position in one way or another. Yes. Delta x, delta y, delta s, whichever one you're using there, that is implying a change of position. So, looking towards t, we're in a kind of similar scenario. We have everything. We need to do a little bit of solving this time, but that's not a huge deal. Let's bring this thing down and let's say, all right, Vf minus Vi divided by A. A, also known as G sine of theta, would be equal to T. 9.8 is indeed positive here. When we plug in this, let me finish this thought and then I will address that. When we finish this part right here, what we end up with is 7.051 seconds. So, talking about how do we determine when it's positive, when it's negative, anything like that. That's where our picture comes into play, right? That's a big part of this thing. So in a case like this, what we are trying to do, if we go back to this slide for a second, what we're trying to imply here, the direction of x is going down the slope. We have said this is what we are going to call positive. If this is what we are going to call positive, and our acceleration goes down the positive direction, then we expect our acceleration to be positive as well. Right? That's what kind of follows from that one. In the other case, when we were looking at dropping the ball bearing from the tower, what we ended up having in a case like this was our acceleration, as we were seeing this thing, was going down. That was a bad A. Our acceleration was going down, right? Versus our y direction that was pointing up. So we had said from the beginning in this problem that y is going up, and we make a decision. We make a decision, we stick with it. Y is going up from the ground. Acceleration, pulling me down, is going to be negative relative to the y that I have just chosen. Depending on the problem, positive or negative, how do you determine which one is going to be which? You get a little bit of intuition from practice with these. My point from earlier on this was that it doesn't actually matter. If I were to flip the direction, nothing would change. I would still get all of the right answers and everything else. Sometimes it's just a little bit easier to conceptualize when it's going one way or another, right? I think it's a little bit easier to conceptualize when we're dealing with a lot of problems where we are talking about the ground and falling down to the ground. It's a little bit more understandable to think about that is up, that's positive, right? That, the floor, is 0. So there's a little bit of intuition that you'll start to build up with it, but at the end of the day, you can actually go either way. If you want to do every single problem with a direction pointing the other way, you know, all of your numbers are going to be negative, but it doesn't change anything. Not all of your numbers, but most of them. So in a case like this, we're following the convention that we had from the last one, where we have x, our positive direction, as going down the slope. So our acceleration, going down the slope, should also be positive. So the last thing that I have for today, we are not getting to the last whiteboard problem because, I don't know, I'm bad at time management. That's what some of this comes out to be, but that's okay. We're going to look at that next time as kind of like a preview problem and everything else, and it's also okay because it's a little bit of a doozy. So we will get back to that one on Monday. But one of the things that you do have kind of associated with this is a short little lab. It doesn't take too long at all, but you can find this lab on Mastering as Moving Man Lab. It's a really short thing. You shouldn't have to spend too much time on this at all, but it's got some fun stuff going on with it, a little bit of simulation to mess around with. If you're in a scenario where you don't have access to Mastering or anything else like that, please do let me know immediately. Send me an email. We can work something out. But otherwise, you can go ahead. All of it is contained entirely on mastery. If you are in the scenario where if you have Java on your computer and you know how to use Java already and all that good stuff, then you're all set to follow that exactly how it is. If you do not have Java, or you have not used Java and don't feel comfortable using random programs, if you follow the link in the slide, if you download the slide, click on this link, it will take you somewhere where it will run in your browser. So hopefully that covers all of that. I can pull up something. It's going to ask you a few different questions on this one, and let me just pull this thing up. It looks something like this. We will end up using quite a bit of these PHET labs. They are wonderful to have. NSF, the National Science Foundation, funded a lot of these out of Boulder. All sorts of good stuff in them. So you've got this person right here, right? Now he's moving. Look at that. I can put him somewhere. I can do something like that. I can slow it down, say deceleration, and send them going. And then it plots out how they would move. And we can find some charts to do a similar thing if we wanted to, if we want to set a lot of these different values. Maybe a slight acceleration or anything else like that. But you've got the chance to mess around with this just a little bit, see how some of these things plot out, and answer some questions about these. But it should be pretty short. And here is our first example of why we don't think about what happens when we actually run into the wall or what happens when we run into the ground. Look at how those graphs change. That is not a very continuous, easy to describe change.